privileged to hear insights from an eminent scientist, Professor N.V. Chalapathi. Sir, on behalf of the family of Royal Global University and Royal School of Environmental and Earth Science, I would like to extend my heartiest greetings to you, sir. Thank you for joining us and giving your valuable time. Moving on, I request Professor B.S. Nibun, sir, Dean of Royal School of Environmental and Earth Science, to give his welcome address. Sir, over to you.
Thank you, Nizamani. Good morning. Welcome, sir. Professor Rao is already well-known geologist who has been decorated with so many fellows. So it will be long to describe about your achievements. So, but you're going to speak. Can you hear us, sir? Is it clear?
Yeah. Your voice is not very clear.
Oh, okay. Yes, sir. That's why we are.
First question. पहले voice ठीक करो भाई. Nothing will go without the clear voice. It's a useful, useless exercise. Right.
Hello. Now is it clear?
Yeah. Now it's better.
Okay.
Yeah.
Better. All right.
Yeah.
So, first of all, I'd like to welcome you, sir, to this talk that we are going to give on decoding the geodynamics of Indian plate by studying flood basalts in India. So, as we know that geology is a very difficult task, and to understand the geology below the earth, even above the earth also, is very difficult. Earth is a mysterious planet. So, in this planet, so much of decoding and you have to do. So this is one of them. See, we are expecting from you that how geodynamics, the Indian plates are happening, and these movements are happening. So our students will be benefited from your talk, and this will be. And for me as geographer, we know a little bit of plate tectonic movements, but the dynamics and will be very difficult for us to understand a little bit. So I hope from your talk we'll be able to understand so many things. Our students will be benefited from your talk. So I would not like to talk much on this. So I'd like to welcome to Royal Global University for giving us your valuable time to us, and thank you, sir. Welcome to Royal Global University, Guwahati.
Thank you, sir. We have with us Honorable Vice Chancellor, Professor S.P. Singh, sir. So before offering my mic to him, I would like to give a brief profile of Professor S.P. Singh, sir. So he is the founder, Vice Chancellor of the Assam Royal Global University, Varanasi. He is presently serving the third tenure as Vice Chancellor of this university. He has been heading institutions of repute since the last 22 years and is having 34 years of experience in teaching and research. Prior to his current position, he was the Director, Sherwood College of Management and Vice Chairman of Sherwood Group of Institution, Lucknow from 2001 to 2009. Sir, over to you.
Good morning, Dr. Rao. Are we audible to you? Are we audible to you clearly?
Yes.
All right. So welcome to Royal Global University, though on the online mode. I wish to see you personally soon. Our invitation is hereby extended to you to visit Guwahati and also to come to the geology, newly nascent established geology department of this university. This department came into existence because of me in the sense that I was not the person to initiate this department. I was quite apprehensive a few years back because geology, somehow, by chance I'm also a geologist, studied from University of Lucknow, the offshoot of Banaras Hindu University. Umakant is a 1 year senior to me who is working with you in your department. So I belong to that department, and I was lecturer in Department of Geology, University of Lucknow till 1996. But then I moved on, and the current head, Hussain Singh, is my batchmate of the geology department. So I'm 1988 MSc Geology. So I'm very, very proud and privileged and feeling delighted, I would say that, not honored to welcome you. And geology came into existence in this university because our chancellor said our vice chancellor's primary qualification is geologist. So we will start geology. Let's try what will happen. And fortunately, we have got many students and many teachers, and I'm very sure that they will bring a lot of laurels to this university in form of projects. And if the projects are not coming in geology nowadays, I think they are mature enough to go for projects, then probably we are not doing justice to the science what we studied. Because I remember my department, and I also know BHU, we are whatever we are today, it is based upon glaciology, grants, everything in the department has been established by different kind of grants from DST and other departments. And I think every year there are at least projects of not less than 5 crores or 10 crores in both the departments. And that kind of geology I have seen. But these are very decent people. I think they will work hard. I'm still seeing them as a budding one. They are, frankly speaking, not working very hard, but they hope they will work very hard, devote extra time Saturdays, Sundays, and other days to submit projects and bring some good projects. They have expertise, but without project expertise is not being reflected in the country and in the world. So that is, I would request Rao Sahab, you can also help this department, associate yourself in some form. We can have some joint projects and other things that will be really, I would say, oxygen or to this department, and we badly require that. A few days back, I was in the University of Lucknow. I told Hussain Singh also to have some joint collaboration. I hope something will emerge out of it. So it's a beginning. I'm very thankful to the department, Professor Mipun and Rajdeep, for inviting you and giving me a chance to hear about the topic. And I remember we used to read diastrophism, and when I was appearing in the civil services examination in 1993, the first question was on diastrophism, and I wrote for 55 minutes, though I was supposed to write only for 35 minutes. I could not qualify, probably only because I wrote more than what is required. So many times we geologists are being obsessed. The knowledge, which is what we carry, probably is not required to be reflected in many examinations. But today it's an academic session. I would love to know and see the best of the things in plate tectonics, or maybe diastrophism, or whatever topic will emerge out of it. So I'm very eager to hear from you. My best wishes to you, and thanks to the department for organizing this online session. God bless you. Thank you, everyone.
Thank you.
Kali Puja.
Thank you, sir. We will try our level best to bring new projects. For sure, sir. So moving on, for handovering the lecture series to sir, so I would like to give a brief profile of Professor M.P. Chalapathi Rao. He is the director of National Center for Earth Sciences and Art System Science Organization, Ministry of Art Sciences, Government of India. He did his postdoctoral work as a senior Alexander von Humboldt Fellow at the Technical University of Klosters-Gellerfeld, Germany. Upon his return to India from UK, he joined Department of Applied Geochemistry, Osmania University, as a scientist full of CSIR, and later as a scientific officer at the Ore Dressing Division of the India Bureau of Mines, where he served almost for a decade. He subsequently moved over in 2007 to the Department of Geology, Banaras University, Varanasi, as a reader, became an associate professor in 2010 and a full professor in 2013, and is continuing in that position, where he has joined NCESS as director for 5 years on deputation. Professor Rao has immensely contributed towards the petrogenetic aspects of small volume potassic to high potassic rocks such as kimberlites, dendrophytes, and your entrained geologics, including diamonds. His researchers addressed their role in unveiling the large-scale geodynamic processes of the Indian Shield, including the composition and evolution of its subcontinental lithospheric mantle, origin and original spatial extent of the Mesozoic large igneous provinces, and the Proterozoic sedimentary basins. He has also contributed to the study of mafic dikes and dike swarms, alkaline rocks, and mass extinctions associated with the Cretaceous Tertiary boundary. Professor Rao has set up state-of-the-art electron microprobe analyzer and scanning electron microscope facilities at Banaras Hindu University from his own grants as PI from DST CERT, and these national facilities are well utilized by students and
Francis and
he has also served as editor-in-chief of the Journal of Earth Sciences, Indian Academy of Sciences, and editorial board member of a number of journals such as Current Science, Geological Journal London, Indian Journal of Geosciences, Indian Journal of Geology, etc. He also served previously on the editorial board of the Journal of the Geological Society of India and Himalayan Geology and Journal of Indian Geophysical Union. Professor Rao is a recipient of National Merit Certificate from Ministry of Education and Culture, Government of India 1984, University first rank holder at bachelor's and master's degree, and triple gold medalist at master's, overseas research scholarship by Asian of British Universities, studentship award by Cambridge Philosophical Society, National Mineral Award Geochemistry, individual category by Government of India, Nagarna Gold University of Mineralogical Society of India 2007, Krishnan Gold Medal by Indian Geophysical Union, A. Naha Award by the Geological Society of India, and many more. So now, sir, I would like to request you to start your session. Over to you, sir.
So very good morning to all of you. I hope I am audible.
Yes.
Okay. First of all, I would like to thank Professor S.P. Singh, the Honorable Vice Chancellor of the University, for choosing to invite me for this talk. And I am very glad to know that he is from Geological Fraternity, from product of Lucknow University in Geology. And I'm very happy to hear about that. And I am also very impressed by looking at the website of your university. I just visited because, to be frank, till Amarjyoti invited me, I was not much aware of this institution. But I can see that it's doing very well, very vibrant institution, a lot of, eminent faculties in it. And even today, I can see a lot of students and audience of geoscience and allied branches who are sitting there. And before my talk, I would like to say that earth science is a science of today. Since last 20-30 years, lot of changes have happened. And earth science is one of the most sought after of the basic sciences. Because at Banaras Hindu University, what I can say is, people leave physics, chemistry, bioscience to enter earth science for a number of reasons. The first thing is they get straight away employment, either in public sector or in private sector. The second, the relevance of earth science is much more today. You look at the landslides or extreme events which are happening, the earthquakes, the volcanic eruptions. Of course, in India we don't have many, but all over the world, the importance of earth science cannot be underestimated. And we have a Ministry of Earth Science to which the NCESS, where I belong. So I always tell students that you don't have Ministry of Physics or Chemistry, but we do have Ministry of Earth Science, which talks about the importance of earth science. So I am very happy that many students are taking to earth science nowadays. Almost every university has earth science. All IITs, either they have earth science. And the universities like you, I am sure all of you prepare very good students to come into the mainstream and they contribute to system science. So I am going to share my screen for my talk. Thank you. So, the topic I will be talking about next 40 minutes is on decoding the geodynamics of the Indian plate by studying Deccan traps and associated volcanic rocks. And in this area in which I've been working since a few decades, and I thought some aspects of this research can be shared here. So the picture, you can also see the NCESS at Trivandrum. This is the campus of NCESS. It's located in a 14 acres of land, and it's one of the oldest science institutes of country. In 4 years' time, it will be completing its 50th year. So this is the slide number 2. So what I'm basically going to talk about is a term which is very prevalent today, large igneous province, which includes the Deccan traps, the Rajmahal traps, which are very close to you, and Banana flood basalts and all the flood basalts. Today we use the word large igneous provinces. We'll see why this term has to be used. What are their characteristics? How they origin and what is their importance? Actually, they are very important. They played an important role in mass extinctions. We all know about the demise of dinosaur and all that. They played an important role in leading to mineral resources, and they also played a very important role in influencing the lithosphere, the Earth's lithosphere. That's what we are going to discuss. We are going to see. Then the third point is I will be talking about alkaline rocks which are associated with them. Then the focus will be on the research which has been done in the last decade and what are the future directions. So this is going to be the outline of my talk, and I'm showing you here 2 photomicrographs under microscope of an alkaline rocks. So you can see your biotypes which are present here. Just I thought they should be very familiar to you. Can you see the slide number 3?
Yes.
Yeah. Now, if you look at this global map of the present day global map, you find a lot of pink colored patches which are shown all over the world. You look at India, I mean, they occupy a major portion of India as well. But if you look at many parts, you go to Siberia and Russia, there's a huge patch. All of them are what are known as large igneous provinces. They are present in continents. You see South America, they are called Parana. Or they are also present in the oceans. You look at Pacific plate, you find plenty of such patches. And you see, you come back to our Indian Ocean, you find Kerguelen, you find such patches. So all of them, we call the term which is used to refer to them is large igneous province. Now this is the Deccan traps. If you look at Indian geology, there are 2 features which stand out, and everybody in the world, the global scientific geoscience community is aware of them. One is the Himalaya and the other one is the Deccan traps. So we all know Deccan traps erupted at around 65 million years. That was the time when India was marching forward from the Gondwana land. Himalayas were not formed at that time. India was going ahead, separated from southern latitude from Gondwana continents, and Deccan traps erupted around 65 million years. This is the landscape of the Deccan traps. Now this word large igneous province was coined in 1991. It's not a very old term. This was coined by 2 scientists, geologists, Prof and Decoding. What they tried to define them, they said these provinces have an aerial extent of almost 0.1 million square kilometers with huge similar volumes of magma eruptions, and they have a lifespan of 50 million years. That means the eruptions happened around 50 million years. And the important other point is they are all intraplate settings. That means they are away from the plate boundaries. You are all aware that modern day we have plate tectonics, which drives the planet Earth, but the plate boundaries where we have mid-oceanic ridges or subduction zones, they have nothing to do with large igneous provinces. because if you go back to the screen here, you can see they're all away from the plate boundaries. They are within the continents. You can see either in oceanic plate or in continental plate. So that makes them very special compared because they are beyond plate tectonics. So these large India's provinces, then people started looking at them in a very different way, and they realized not only in the Cretaceous, but even in the Archean time, we had such provinces. So what they comprise? They comprise the continental flood basalts. In continents, we call continental flood basalts like Deccan Traps. In oceans, like in Java, we call oceanic plateaus. We have submarine ridges. We have seamounts, ocean basin basalts, etc. All of them come under LIPs or large igneous province. They can be volcanic, they can be plutonic as well. That means they can be very coarse-grained in nature. And in nature, no two LIPs are alike. Like you take Rajamahal traps or Deccan traps, you find a lot of chemical, a lot of geochemical, geological dissimilarities between them. Now, as I said, some of the characteristics of these large igneous provinces are they can be massive to ultramassive in composition and aerial extent. You have already seen they are intraplate in nature and they are in place up to 50 million years. But recent studies have also shown some of the large igneous provinces, their pulses can range from 1 to 5 million years. And recently, geologists have recognized they are silicic large igneous provinces. Silicic means they are dominated by silica-rich magmas or rock types like granites, rhyolites. The Malani igneous rocks, which are present in Rajasthan of India, is a classic example of silicic large igneous province. And people have realized over the years that these large igneous provinces are also associated with rocks like alkaline rocks like carbonatites, which have the highest rare earth elements of all the igneous rocks, and kimberlites, you all know that they contain diamonds. So let us look at some of the world's well-known large igneous provinces. Like I've shown some pictures. These are Siberian traps on the extreme right side, and you have Deccan traps in the middle. You have Columbia flood basalts on the left side. You have these are some of the world's very well-known LIBs. Columbia river basalts, Kivina one basalts. Again, they are Precambrian in Canada. You see, Columbia Miocene age. The Deccan traps, our own Deccan traps are Cretaceous to Eocene. In Brazil, you have early Cretaceous Parana traps. In South Africa, early Jurassic Karoo traps and the Siberian traps are Permian to Triassic, and they are of similar age as the Punjab traps in Kashmir of India. We have traps which are called Punjab traps, they are of exactly similar age. As is told you, they are associated with silicic magmas also, silicic LIBs are also present. For example, the most famous one is your Snake River Plains in Columbia River in US, whose age is it's a very young LIB, silicic LIB. It ranges from present day to 17 million years. So this is where you find silicic volcanism very, very rampant in these parts of US. Yellowstone National Park, very famous geological heritage site. It is one of the areas where this, which present in this silicic LIB. Now, so how to explain a silicic magma coming from a massive, rich basaltic type of material? So there are different models which are given, because if you look at Malanis, for example, in Malanis you have a lot of massive magmas, you also have plenty of silicic magmas. How to explain both of their combination together? So there are two ways to explain it. One way is you have a huge mantle plume which is coming from core mantle boundary. As it comes up, it can melt the peridotite and it can lead to basalt magma. And as the plume head pushes up, it can also melt the upper crust, which can give rise to rhyolitic bed. So that's how geologists try to explain one way that both these magmas occurring together. The second way is, you all know from Bowen's reaction series, a basic magma can differentiate and it give to a silicic magma. Even that process can also take place. But the point is, in many of these LIPs, like in silicic LIPs, you also find your basic magmas. Like I talked about Malanis. This is the Malani. If you go to Rajasthan, Aravalli Craton, you find plenty of these silicic volcanics associated with mafics. They are Neoproterozoic in age. They are around 750 million years. We call Malani years too. So Malanis, people believe that they are formed when India and Madagascar and Seychelles were separated, and this magmatism happened in the initial breakup. It happened because today you can find this type of Malani volcanics in today's Madagascar and also Seychelles. So when all of them were together, these Malanis were erupted, and later on we know that Madagascar and Seychelles were separated from India. So this LIP, Malani LIP, is a non-subduction setting, nothing to do with plate tectonics, dominated by calcaline igneous type of rocks. It is mafic magmas are also present, but what people have not found is the hidden mafic magma. What is the magma chamber today is not known for one reason, because it is covered, the exposures are covered to a great extent by Thar Desert, and geophysical studies are few. Now, another interesting aspect of these large igneous provinces is you find carbonatites, kimberlites, and lambrophytes. So these three very rare alkaline rock types, you all know, they are very, very sought after due to their economic promise. They are all associated with this large igneous province. For example, if you look at the Deccan tracts as an example, this is the present day example of Deccan tracts, exposure of Deccan tracts. You find your Ambatonga, India's one of the largest carbonatite, is located in the Deccan Tract province, and it is of the same age. If you come to Bastar Craton, here you can see you find Bahraini Godumati kimberlites, which are 65 million years and they are very rich in diamonds. So all of them are associated with the Deccan large igneous province. Like in Rajmahals, traps which are in your backyard, you find Rajmahals, you all know, are 1.7 million years. So then you find a lot of reliquites, lambrophytes, which are associated with the Rajmahals. Of course, nobody has reported diamonds from them so far. So the thing is, what is the relation between these alkaline rocks and the large igneous provinces? So we did a lot of work. I just want to summarize what we have done here. That what we feel is when the mantle blooms come up from the deep mantle, they create heat, and that heat is also responsible for the melting of this metasomatized lithospheric mantle around 150 kilometers depth, where diamonds are stable. So these magmas are generated from that depth. So the role of mantle plumes in the generation of alkaline magmas associated with large igneous provinces is today more or less accepted. So we need to have a plume to explain the alkaline rock large igneous province association. So coming back to large igneous provinces, as I told you, what is the age of Deccan Tracts? If somebody asks you, if you say it is 65 million years, it is not really true. 65 million years is the time span where bulk of the Deccan Tracts were erupted. But if you see the ages which are available for the Deccan Tracts, you will find the first phase started at around 67.5 million years. And later on, second phase started where 80% eruptions happened, and there is a waning phase at 64.8 million years. So the large igneous provinces apparently are pulsed in nature. They don't happen in a single stroke. They happen in a range of time scale having multiple pulses. And this is a record not only from Deccan. If you look at different large igneous provinces in the world, the same scenario emerges. They were erupted in different phases in a different time spans. So as I told you, you have large igneous provinces in the continents, you have large igneous provinces in the oceans, and you have large igneous provinces which can be of silicic nature and as well as mafic nature. And I gave you an example. Your Malanis in India are a classic silicic LIP, and mafic LIP, of course, our Deccan Tracts, Rajmahal, they come under it, your mafics. Now, people, scientists have also discovered or discovering the presence of such large igneous provinces in our planets. Like Mars, a lot of work is being done on Mars, and there are two regions which are mentioned here, Tarsis and Alzheimer regions, where people suspect there are large igneous provinces present. On Venus, Artemis is a region where, based on imageries and all, large igneous provinces are suspected. And of course, on Moon, you find lot of basalts. Now, these are we call mare basalts or lunar mare basalts. Of course, on Moon there is no plate tectonics, but here the large igneous province might have been formed due to extra terrestrial impacts because there is no plate tectonics here, nor there are any mantle plumes known on the Moon. We don't know how this many basalts have been formed. One of the most important mechanisms which is invoked is there was meteoritic impact on the Moon which gave rise to these basalts. And even geologists suspect that Jupiter's satellite Io also has an LIP. Now, we talked about LIP, large igneous province, but there are a lot of other magmas which are not LIP magmas. We need to acknowledge them. The most important thing, which every student of geology knows, are mid-oceanic ridge basalts. They also are erupting continuously at plate boundaries, but they are not considered as LIP for the simple reason I told you. LIPs have nothing to do with plate tectonics directly. Orogenic batholiths, you have Bundelkhand granite, you have Singham granite, they are all huge volume magmas, but they are not LIPs because they are all due to your subduction type of process. Sea mounts, submarine ridges, they are all nothing to do with LIPs. So we need to distinguish that the type of magmas which are found on the Earth's surface, not all of them are due to LIPs, but they can be of different types or different origins, like related to plate tectonics. Now coming to the topic, how LIPs are formed. You know, in Earth science, as your Vice Chancellor has said, there are so many dimensions. I mean, there are several models. I would like to place before you few working models which people believe can explain the origin of LIPs. The first one is plumes. Mantle plumes are thermal material, high temperature material, which come up from core mantle boundary, and as they come up due to buoyancy, they can come and they can bombard with the lithosphere and the oceanic or continental, and they can lead to your LIPs. So this is one model which can explain how large igneous provinces are formed. That is the plumes. Like Deccan, perhaps we think that they are formed due to Indian plate passing over a plume called reunion hotspot, which is present today. But again, as I said, these are models which are accepted, but there are so many questions on that. So plumes can relate to your large igneous province. So if you take this map, you can see global map, you see different dots. All these dots correspond to different plumes, hotspots which are present today. Now, splash plumes are those without plume head. A plume can have a big head, like your mushroom, or today many people think some plumes may not have such plume head. But irrespective of that, all such hotspots, whether they are having plume heads or splash plumes, can really lead to the eruption of the Deccan traps or any other LIPs. The second mechanism, what the geologists invoke, that how LIPs can be formed, is due to a process called lithospheric delamination. You know, lithosphere includes crust and upper mantle. So when subduction happens, your uppermost material will get subducted, and that material becomes a high density rock which we call eclogite. Because the density is very high, it delaminates. Delaminates means it breaks off. It sinks in the mantle, and due to its sinking, the mantle is very hot. It tries to melt and it tries to come up again. And so people think that delamination leading to agglomeratization, sinking and rising can also give rise to your large igneous provinces. So this is the second mechanism, like people invoke. The third mechanism by which LIPs are invoked is due to paleosubduction. I told you in the beginning of lecture, LIPs have nothing to do with plate tectonics. But here what I am talking about is a paleosubduction. That means due to plate tectonics, a plate somewhere in the world has subducted and it has gone down. We call it a stagnant slab. After millions of years, this slab melts and it melts, come up, and then they lead to flat basalt volcanism. So subduction is not happening actively, but it is happening passively. So people think, like Ivanov, that this type of model can explain Siberian traps. Why? Because when they analyze the composition of the Siberian traps isotopically, they have found subductions in natures in there, which are very difficult to explain by a simple flow model. So that's why Ivanov et al. 2015 suggested a precursor subduction can also be responsible later on for a LIP eruption. And the fourth model by which LIPs can form, large GPS provinces can form, is by impacts, meteoritic impacts. Actually, which impacts have happened throughout the Earth's history, but these are very rare. And that's why, when compared to the human life, the impact frequency is very, very less. So any event, geological event, which happens in our lifetime, we can appreciate it. If it doesn't happen, we don't bother about it. Like tsunami. Tsunami of 2004 or 2005 which came up. Before that, except geologists, nobody was knowing what a tsunami is because it never happened in their lifetime. But once it happened, now everybody knows that tsunamis are generated due to your deep focus earthquakes in the oceans, and there is a chance of getting tsunami whenever a magnitude of 6 exceeds on Richter scale. Likewise, your impacts played a very important role in shaping the Earth's surface. Actually, the moon, our own satellite, is believed to have been separated from the planet Earth due to such an impact. So, this type of impacts can lead to mantle melting, and they can also lead to large amount of magmas. So, as I told you, impacts are used as very important mechanisms to explain the LIPs in extraplanetary systems because there is no tectonism there, no plumes there. But on Earth, we are on the planet Earth, so far we are not aware of any model except for Java blood LIP, where people think that because there is no mantle flow, there might have been a bolide or your astrobleed or meteoritic impact which happened. Now, what we have seen so far is what are LIPs, what are different types, and how LIPs can be formed. There are 4 ways, maybe there are many other mechanisms, but we are so far aware of at least 4 mechanisms which can be responsible for LIP generation. Now, why study of LIPs is very important? Because it tells you about paleogeography. But paleotectonic or paleocontinental reconstructions can be done very elegantly by using LIPs. For example, you take this some X continent, it has broken up into craton A, craton B, but the LIPs on either side, they are remaining there itself. So if you can get the LIPs, if you know the chemistry of LIPs, you can establish that these 2 cratons A and B were together initially and they got separated. So people use fossils to date to make this paleogeographic reconstructions. People use paleomagnetism, but LIPs also, if you paleomagnetically date them and if you have geochronologically, are very, very important tools to reconstruct past continent configurations. As I told you, this is a cartoon showing the geological time scale where 5 major mass extinctions happened in the Earth's history. You see, there were major extinctions in the Earth's history. The most famous one we know is the Cretaceous Paleogene when dinosaurs were extinct. But even before that, there were several extinctions. You can see here 250 million years, you had Permo-Triassic extinction, then you have Triassic-Jurassic extinction, then you had another extinction in Jurassic. So, what is the cause of this mass extinction? There are at least 2 ways by which mass extinctions can be explained. One is by the eruption of large GPS provinces. As you have seen, large igneous provinces can erupt over millions of years, 10 to 5 million years. Imagine the amount of carbon dioxide, the amount of sulfur dioxide, amount of all deleterious gases which are pumped up for millions of years in the atmosphere. It creates a greenhouse effect and it can kill the organisms. So that's why people looked at large igneous provinces as one of the mechanisms for the eruption, for the demise of the. So such technical glitches, they are quite common in daily life, so we need
Yeah.
to go ahead.
Yeah.
So these are all the alkaline rocks, and there are at least more than 400 igneous rock types, which are given names are given for the alkaline rocks. So, I mean, I mentioned only few. So, if you see this slide, I don't want to go into the details, but you can find the names like Besanite, Ephrite, Eucydite, Nephelinite, Izolite, Comendite, Shoshonite. They're all different examples of alkaline rocks, and we name the alkaline rock based on their minerals, which I mentioned, the presence and abundance of the minerals like nepheline, eucite, olivine, and so forth. So I just thought students should be exposed to these alkaline rocks because they are important economically and also they have a lot of geodynamic significance. So if you look at the rare earth elements are most sought after economic commodities nowadays. China has the world's largest rare earth resource, but last 3 years, China has closed its market. So all over the world, people are looking for rare earth resources because they have tremendous applications. And if you see the rare earth element contents, you can see a more mid-oceanic grit basalt. This is a rock scale on the y-axis. On the x-axis, you have the rare earth element. You can see how rich the alkaline rocks like kimberlites, orangites, lamproites are compared to the mid-oceanic grit basalts or OIB means ocean alien basalts. They can be 200,000 times more than that of a chondrite, which is a meteorite. So that shows the abundance of rare earth elements in alkaline rocks compared to normal terrestrial rocks or even a meteorite. So, how alkaline rocks are formed? So, this is a big issue. The one important mechanism, as I told you before also, that your mantle plumes can play a very important role in fertilizing the lithospheric mantle. We all know that the Earth's upper mantle was depleted in crustal formation. That means when the Earth's crust was formed, from where it was formed? It was formed from the mantle. Many of the elements which were there in the upper parts of the Earth's mantle have migrated into the crust, and as a result, the upper mantle is very depleted. That's what we call depleted lithospheric mantle. But these alkaline rocks, they come from such a depleted mantle. So now comes the question, how come a depleted mantle is giving such alkali-rich magmas? So this mechanism, this term, mantle metasomatism has come up. Mantle metasomatism means refertilization of the Earth's mantle to give way to alkaline rocks. So this can happen either by mantle plumes or by subduction. That's why mantle metasomatism is an essential precursor to alkaline magmatism. But some people, some geoscientists also think that mantle metasomatism is a consequence of alkaline magmas. That is, your alkaline magmas can also, their formation leads to mantle metasomatism. So it's like a chicken and egg problem, how you look at it. But the point is, to generate alkaline magmas, you must have mantle metasomatism. Otherwise, you can't explain the abundance of alkalis in the depleted mantle. Now we go back to the topic that is alkaline rocks from the Deccan large igneous province. So this is the exposed Deccan traps of India, that V. This is the grey color V. And in this you find lot of white stars. They are all alkaline rocks which are associated with them. They include your carbonatites, lamprophytes, and the rock types I mentioned in the chart. They are all associated with these flake basalts, that is the Deccan traps. Now we did a lot of work on them. I'll show you some field photographs. Geology is basically a field science. unless you go and see these rock types in field and make their thin sections, you don't really appreciate. But the areas on which my students have done their PhD and where I work, I'm going to take you to there. The first area, some of which of course I didn't work, it is from the literature. This is an alkaline province, alkaline rocks which are associated in the northernmost part of the Deccan. You see, this is called Muslim Bagh ophiolite area. This is now in present-day Pakistan here. Then this is the Bastar area, Bastar Craton. You find alkaline rocks of Deccan age which are found as kimberlites. Then if you go to here, this is the Chota Udaipur area where you find Amba Dongar, Dongar Dom, Fidai Mata complexes which are located. And this is another area, it is very close to Bombay, the city of Mumbai, where you find a lot of alkaline rocks like Janjira, Murud. This is another area. And if you go to Gujarat, you find the famous Girnar complex, Mount Girnar complex. It has a lot of alkaline rocks. You have also Barda Hills, Osam Hills. They find a lot of alkaline rocks associated with the Deccan. Then if you go to Thar Desert, you find Dandali and Sarnu, where you find carbonatites. And India's richest carbonatite, your Geological Survey of India has discovered at a place called Kamtai, which is located here. And if you go to Bhuj area again, where we had earthquake, Republic India earthquake in early 2000, 2001, there also you find alkaline rocks. So the Deccan alkaline rocks are classic examples where LIPs and alkaline rocks are co-spatially associated with each other. And another area is the Munwara area, where you find these alkaline plugs, Toba, Mer, and Munwara, which are associated here. First, I field photographs.
So now I have to leave now. It was very, very interesting to hear you. I have a meeting at 11:30, so I will be excused. Because we will talk and I'll take your number and we'll connect.
Yeah. Thank you, sir. Thank you so much.
I will get connected after I come back from the meeting. I will join. So somebody should order my behalf. Thank you so much.
Okay. So this is the Mount Girnar. Mount Girnar is the highest topographic point in the state of Gujarat, where you find a lot of cyanates, nepheline cyanates, and lamprophyres which are associated. So these are occur as composite dyes. So the students can look at closely. A lamprophyre LP is associated with cyanate as a common plug. So this shows that there must be a relation with their magmas together. Again, a lamprophyre and nepheline cyanate together. Another lamprophyre without nepheline cyanate, which is occurring as a dye here. If you go to Munwara complex, again, Munwara complex intrudes Erinpura granites. Erinpura granites are Neoproterozoic in age. You find a ERG is Erinpura granite. A lamprophyre is cutting across this granite. You can find it here. Then again, you have your nepheline cyanates and all associated with the Munwara complex. If you go to another alkaline complex called Finai Mata, this is the Finai Mata hill, this is Fulla Mata hill, you can see. These are in the near Baroda, Chota Udaipur area, where again lamprophyres cut across the Deccan tracts, and you can see this is the strike of the lamprophyres which are present, and you can see them in very close look here. Again, this is my student, who is sitting, Samarendra Sahu, who is now in Shillong, GSI Shillong. He did his PhD in this area. Then if you again, lamprophyres are very peculiar rock types. They are alkaline rocks, but lampros means shining, fire means dry. They contain huge phenocrysts of amphiboles, pyroxenes, which can be appreciated on megascopic scale. You can see here, they are all present. And these lamprophyres are cutting across your cyanates and basalts in Chota Udaipur area. Here, this lamprophyre dike is cutting across your Godra granite in Chota Udaipur area. This is the Kamsai carbonatite. As I told you, it is India's largest carbonatite deposit, which has been discovered by Geological Survey of India. One of my students is doing PhD on this genesis of this carbonatite. You can see here, this carbonatite has lot of what you call stringers of calcite veins. They are all calcite veins, and this is the desert. Kamsai is located in the Thar Desert, you don't find the exposures of the country rocks. They're all soil covered, but this exposure has been, it's in a pit, this occurrence is exposed. So if you look at the ages which are available for the alkaline rocks from the Deccan traps, you can see these are the available ages. The ages range right from 76 million years, that means much before Deccan traps erupted, till along with the Deccan traps, and even they postdate the Deccan trap eruptions. So the LIP Alkaline Rock Association is very important in the sense that alkaline rocks predate the LIPs like in Deccan trap, they postdate the Deccan traps, and they can also be synchronous with the Deccan traps. So that means we need to think of a mechanism to explain all of them because all such examples are present. So this is on the right side. This is a spinel lazolite nodule which is present in a alkaline basalt. This is a mantle derived xenolith which have been picked up by this sample. So if you want to read information on the alkaline rocks associated with the Deccan traps, one of the foremost works was published in 1926 by a professor who was the founder of Banaras University Geology Department, K.K. Madhav. This paper was published in Journal of Geology in 1926, almost 100 years ago, that differentiation in Mount Girnar, where he talked about the occurrence of these alkaline rocks in the Mount Girnar. Then in 1972, Professor Subbarao from Vikram University, Ujjain, he summarized the alkaline rocks of Deccan traps and he provided a big review, which can interest researchers and students alike. And Professor Mir Bose, whose textbook on BS petrology is very familiar to students, he has written Alkaline Magmatism in the Deccan Volcanic Province. Here, he showed that alkaline rocks and Deccan traps may be related to a mantle plume. He first time in 1980, he pointed out that you can see in the abstract, all these things point up to a plume activity. That's what he suggested. Then in 1990s, high precision geochronological ages they started appearing for the Deccan traps and alkaline rocks. Professor Ashish Basu from Rochester, he started dating these alkaline rocks and he showed that both of them were alkaline rocks and the Deccan flood basalts, they were all related to a mantle plume because he has measured helium isotopes from these rocks and they show a plume origin. So the plume origin model which was suggested by Bose more or less was confirmed by Professor Bose. And there are many other works which you can see carried out by different people. They carried out petrology, geochemistry work on these alkaline rocks. So people have also done paleomagnetism of these alkaline rocks. You can see here. And they have shown that these alkaline rocks in the Kutch area of the Deccan are some of the earliest alkaline rocks to have been formed. And that means they were formed almost just prior to the Deccan trap eruptions itself. So they are the best areas to sample to these earliest magmatic rocks there. And there are a lot of other studies which have been carried out involving high pressure experimental petrological studies which have shown that the primitive strongly silica undersaturated alkaline rocks, they were generated by high pressure fractional crystallization. It's a model given by Ilanjan Chatterjee. And this is the paper which I was talking about. First carbonatite hosted RE deposit from India at Kanthai, which was discovered by S.K. Bhushan of GSI. Later on he joined your MSPL company at Postpaid. Anyway, these are different papers. I don't want to talk on those papers, but I want to summarize that alkaline rocks in the Deccan traps, we have recently made a comprehensive study and we divided them into different provinces. Kutch province, Saurashtra province, Gujarat Central, Chhotaudepur province. You have Mumbai Trombay province. I showed all the maps before you. And Central Deccan province, where your kimberlites of Kodumali, Varanasi of 65 located. Aravali province, where Muruvara, Samudandani, Kamtai come. And even in Himalaya, Ethiopian Himalayan province, I talked about Muslim Ophiolite, which is in present-day Pakistan and Quetta, where alkaline rocks associated with the Deccan lavas are associated. So, alkaline rocks are very important components associated with the Deccan traps. Now, I want to highlight some major advances which were made in the recent years, which might definitely interest students. The first major advance is the polychromous nature of these alkaline complexes. That means these alkaline complexes were also not erupted in one stroke. They were erupted over a protracted period. That evidence has come from Mundwara complex and Sarno Dandali. Researchers from IIT Bombay, when they dated different rocks in the Mundwara complex, they got two age groups. One is 90 million years, one is 65 million years. That means this alkaline complex was in place over a protracted period of time. Exactly similar thing has been noticed for Sarno Gandhari, who are getting ages of 90 million years and 66. That means not only the Deccan traps, but the alkaline complexes themselves were also erupted over protracted time scales. That means all the models which were given so far did not consider these aspects, and we need to look at them from a different aspect. The second important thing is, of course, there are alkaline rocks which are older than Deccan traps, but bulk of the alkaline rocks are erupted close to Cretaceous Paleogene boundary, that is 65 million years. You take Gimla, our work, or you take Parisio's work in the other alkaline rocks, many of them are associated with 65 million years, that is Cretaceous Paleogene boundary. Now, the third important major advance which has been made is this Kamtai carbonatite, which is considered to be India's richest carbonatite, RE-hosted carbonatite deposit. We have dated them just 2 years ago. My student Sudeepa Bunia, she is doing PhD on that, as I said, and that age is exactly similar to 65 million years. That means there must have been a relation between antique plumes and RE metallogeny. Also, carbonatites, you all know, are the rock types which have a lot of carbon dioxide content. And this release of carbon dioxide content, the KBG boundary, might have contributed to mass extinction there along with Deccan traps. That's what we have proposed. You can go through this paper in detail. So, how we dated the complex Kamtai as we separated few zircons. These are zircons, you can see, these are zircons we used shrink technique, that is a ion microprobe technique to date. The circuits are the places where we have used shrimp technique to ablate the zircon, and we have obtained ages which are around 68 to 65 million years, you can see, by using uranium-lead dating technique. The other important major inference which has been obtained in recent past from alkaline rocks is the presence of evidence of modern metasomatism below the Deccan traps. This is again a PhD work of my student Rohit Pandey. While doing work on Lamprofas, he came across a mantle xenolith. This is a mantle xenolith of olivine, CPX, apatite, and so forth. And you find a lot of mica surrounding this CPX. You can see here. This pH is chlorobite mica, apatite. So these minerals are extremely important because they contain a lot of volatiles. They are more fusible minerals, and these minerals occurrence in a mantle xenolith suggests that the xenolith did not melt completely during Deccan episode. That means there is direct evidence for modern metasomatism in the subcontinental lithostratic mantle below the Deccan traps. So we did some electron microprobe analyzer studies. We did some X-ray mapping. This technique uses mapping of potassium, mapping of phosphorus, mapping of calcium and magnesium, which establishes these minerals. So based on that, we inferred that modern metasomatism is present. And this modern metasomatism has been further established by the works of other scientists from Pune University. They have also documented subsequently phlogopite and other phases in the mantle xenoliths in a Sarno Gandhari area. All these things show that the mantle below this Deccan Northwest India, where these alkaline complexes are located, is highly enriched and metasomatized in nature. So again, you can see some electron images where these minerals, logopite, your carbonates, they all have been shown and they have been established. So mantle xenoliths are infiltrated by carbonatitic fluids, leading to metasomatism and crystallization of logopites during lifting. And finally, one major advance which has been made in recent times is the discovery of the magma plumbing system. So what exactly lies below a alkaline complex? You and I cannot see because it is not exposed. But the mineralogy plays a very important role in telling you whether you have cumulate type of texture, you have dissolution type of textures. So based on all the mineralogical evidence, we have reconstructed the magma plumbing system in an alkaline complex like Munwara and Finangmanga, and we like growth of pink rims over white coats of clinopyroxene based on cumulates of olivine, growth of greenish brown rim over light brown rim of amphiboles, and so forth. We have established that mixing of different magmas has happened, and through that mixing, based on that, we established the plumbing system based only on mineralogical grounds, like I have shown you here. So, if we look below, what lies below the alkaline complexes, the plumbing system, as I have shown, can be brought out by mineralogy. Your geophysics can also bring out prove the existence of such plumbing systems, and also the presence of plumettes, fossil plumettes can be established. This is in a 3D we are looking at that they can be present below your plumbing systems. So, like this xenoliths information is very important for us because if you find minerals like chrome dioxide, you can estimate the paleo pressures and temperatures, and you can know the thickness of lithosphere at the time when these rocks were erected. For example, this is a chrome dioxide which was recovered from the alkaline rocks in the Bulwara. This chrome dioxide, we measured its chemistry. This is olivine, this is CpH. CpH is a chrome dioxide here. And we calculated the depth and the pressure and temperature from which these xenoliths were derived. So they were all derived from depths corresponding to around, you can see, corresponding to 60 or to 90 kilometers depth. That means we know the thickness of the lithosphere at the time when this Lamprofire was erupted. And likewise, recent studies have shown the presence of crustal contamination in also these alkaline complexes, like work by Hetuseth and all have shown. And people have also discovered pre-Deccan rocks in Deccan LIT, like mid-Cretaceous lamproite, which has been discovered, and also lower Cretaceous rocks have also been discovered from the Northwest India. And these rocks have been dated like 120, 128 million years. So perovskite from this ultramorphic Lamprofire was dated, it gave age of 125 million years. Wow. But it tells us there are alkaline rocks much before the Deccan rocks, and that means what we are thinking, the age of the Deccan rocks 65 to 18 billion years, maybe we need to extend it much further if these are related to such magmatic activity. So this is an unpublished age which we have recently determined from the Munwara carbonate from Munwara complex. Again we are getting 122 million years. That means the alkaline rocks associated with the Deccan traps predate Deccan traps much by almost double the time span, 122 million years to add to 65 million years. So the story is, you can see this was the configuration of India, that was the greater India at that time where this 122 million years, this was the time frame where India was located. So always try to look at the age of the rocks from the position of India at that time. If you look at the position of India, compare, if you place a 122 million year rock in today's configuration, you cannot appreciate the geological setting. Exactly likewise, if you look at Archean rocks, if you imagine today's paleogeographic position, you may not appreciate. Try always to keep it in paleogeographic context, then you can know what was the scenario, what was the things which was happening at that time. So finally, why carbonatites are rich in rare earth elements? Because hydrothermal fluids which are associated with them, they actually sequester the RE, and that's why they play a very important role in controlling rare earth element mineral distribution in rock lakes, carbonatites. So these works have also been done in recent times from IIT Kanpur group, hydrothermal fluid assisted mineralization to Deccan magmatism. Likewise, genetic models have also been given for RE mineralization in Ambagunda carbonatite complex. So finally, whatever geological information has been given, it is based on your mineralogy, based on your field evidence. But if you find good support from geophysics, then we get a very good picture. So this is a paper recently which has come up by Dept and others from GSI, where they have actually brought out concealed architecture like plumbing systems based on aeromagnetic surveys and so forth, which establishes the petrological models which have been given by us. So where the future lies in LIPs and especially alkaline rocks associated with LIP, the young people can work on that. So what exactly is the Deccan element? What exactly are Deccan traps? Even now it is not clear. Are these rocks of 65 million years or are these rocks of 122 million years? Because you are seeing alkaline rocks which are associated with the Deccan date back to 120 million years also. What is the relation is even now today it is not clear. Lot of work can be done on high quality mineral chemistry work can be done, on isotopes can be done, on mineral scale. Nepheline cyanides are very important resources for errors. People can do research in this direction. Plumbing system of alkaline complexes can be established. Geochronological information on several alkaline rocks is lacking. There is a lot of scope so that more better models can come up and dating of metasomatism can be done. So before I finish off, I want to tell young students, especially those who intend to do research. This is a famous quote by Michael Faraday. Whatever you do, you try to finish it and try to publish it. Publishing in good journals, publishing in SCI journals is of paramount importance to make a mark. So don't forget it. Work, finish and publish. It's a very important thing. And I take care of, I was the chief editor of Journal of Assistant Science, India's leading essay journal. Now my tenure got over, but I'm still associated with the journal. If anybody has got good research findings, they can consider submitting to this journal. It is impact factor of 1.92, India's most acclaimed science journal. And anytime any students from you, they can come to NCESS for any. We have very good facilities. They can do internships, they can do PhDs, and they can use the facilities for their research. Always they are welcome because all these facilities are meant for youngsters. So with this, I think I should put a full stop. It's 12 o'clock. So I tried to share with you what are LIPs, what are alkaline rocks, what we know about alkaline rocks of Deccan traps. This is a lecture which I give in a semester. So I try to condense it in 1 hour so that the students can get benefited. At least to some extent. I know it's not possible to synthesize everything in 1 hour, but I tried my best to place before what is important. So thank you very much.